Hey everyone, welcome back to my Calculus 2 series. In today's lesson we're going to be talking about sequences. So the idea of a sequence is fairly simple. It can basically be thought of as a list of numbers that are ordered. So something like this. Let's say we have this sequence from A1 all the way to AN. The key thing to note here is that it is ordered. So this sequence right here can be written in two different ways. One of them using the curly braces right here. And you basically just put the term there, so A of n. And another way to rewrite that would be, again, to use these curly braces and put A of n. However, this time you would specify the bounds on n. So all this would mean is that it's going from n equals 1 to n equals infinity. So another way to write sequences is by giving the nth term. So I'm going to show you an example of how we can do that, but basically what I'm about to write here are three sequences that are equal to each other. So the first one, let's say we had a sequence where we had n over n plus 1, and then this would span from n equals 1 to infinity. Now this is equivalent to saying A of n is equal to n over n plus 1. Again, this right here is the definition that I was talking about. Sometimes it's enough to give the nth term of the sequence. And obviously the last way of writing it would be to fully express the sequence, which again we don't really do often, but you would write like, okay, the start term would be a half, then it would be 2/3, then it would be 3/4, and so on all the way until n over n plus 1, and then maybe there's some more over here. So as you can see over here, these three are the exact same way of writing it. Obviously this is a little longer than the other two methods, but yeah, these are all valid ways of expressing the sequence. Now the question we try to answer a lot of the times is, what term is this sequence approaching? So what is the last term in this sequence? And obviously if we were to continue a sequence like this, well, when would it stop, right? Well, it would stop, as maybe you could see here, is that it would stop at n equals infinity. And obviously that's a fairly large number. We can't just plug in, okay, n equals 10,000, n equals, I don't know, 1,000,000 or something like that. We need to figure out a way to set n equal to infinity. And we sort of know how to do that already. All we need to do is we need to take the limit as n approaches infinity of the sequence term, which is right here. So of the nth sequence term, because we want to set the nth value equal to infinity. We basically want to find the when n is equal to infinity, what is the value? So then we plug n equals infinity into here, and we want to take the limit of n over n plus 1, and we figure out what this limit equals. Obviously it's pretty easy to see that this limit is going to equal to 1. We have now found the answer as to what these three sequences right here go towards, and that this process of going towards a certain value is called convergence, and we're going to discuss it shortly. So moving on to convergence and divergence, we have talked about this in some previous lessons, but the concept again remains pretty much the same. Basically, if the limit of the nth term of a sequence exists, then we say that that sequence is convergent, or the sequence converges. Likewise, if the limit does not exist, then we say that that sequence is divergent, or it diverges. Now what that would mean for a convergent sequence is that the terms in that sequence would actually approach a certain finite value. In this case we call it L, capital L right here. And for a divergent series, as we can see, the terms would go off somewhere to infinity and basically be a value that we can't compute. Now as you can see, for sequences we don't actually draw functions, meaning those dots are not connected. And the reason for that is that n is actually a set of, like, n belongs to a set of integers, meaning that n will only be like 1, 2, 3. It'll never be like a like 1.5 or like, I don't know, pi, for example. It'll always be an integer value, meaning that we get these kind of like discontinuities. So yeah, when we draw out these sequences, we generally use points to denote what the values will be. So now on to convergent sequences, and we've seen this a lot. Like, these laws stay the same for like integration and differentiation, so they're very similar. That's why I'm kind of going to just quickly explain them. But yeah, these laws should like you should see a lot of similarity between these laws and the laws we've previously learned in this course. So we assume that we have these two convergent sequences, A of n and B of n. The important thing is that they are both convergent, otherwise these laws do not hold. And then we assume that there's some sort of constant called C. And then any combination of these laws will sort of give us convergent sequences as well. So if we have the addition of two sequences, well, that will also be convergent. If we have the difference of two sequences, that will also be convergent, provided, again, that both of the separate sequences are convergent. If we have an integer multiple of a sequence, that will also be convergent. If we want to multiply those sequences, that will also be convergent. And again, for the division, this will be convergent provided that the bottom is not equal to 0, so the limit of the B of n, or kind of the second sequence, is not 0, because we don't want that division by 0 error. And then also, if we have a series to the power of something, in this case p, it's going to be equivalent to this, but it's also going to be convergent. We just have these constraints that b is greater than 0 and a of n is also greater than 0. Naturally, you might ask, how do we add two sequences, or how do we subtract two sequences? So I'm going to pick out two random sequences, and I will kind of show you. So let's say that the first one is going to be, I don't know, 1, 2, 3, 5, 8, 13, and so on. Some of you might recognize that as the Fibonacci sequence, and we'll say that this is A of n. Then we'll say that B of n is equal to 3, 4, 5, maybe 3, 4, 5, and so on. So as you can see, neither of these sequences are convergent, and the reason being that this one right here actually doesn't approach any value, because it's going to be the sum of the two previous terms. We'll just be getting a value that's larger and larger. As for the second sequence, we can see that we just alternate between 3, 4, 5, 3, 4, 5, and so on. A of n plus B of n, well, that's going to be pretty simple. It's you simply just add these two terms. A of n minus B of n, well, that should also be pretty simple. And then the multiplication of these two, again, pretty simple. It would just be, we're basically just doing it term by term like this. And obviously for the last one, it would be an over bn. In that case, we just need to make sure that we don't have a 0 anywhere. So there you go, that's some basic operations with these sequences. And again, these laws right here will hold for them, provided that both of them are convergent. In this case, they're both divergent. So the laws won't hold for any of these right here. So another thing that we have learned in previous lessons is the squeeze theorem, and we can apply that to sequences too. If we have three sequences right here, and we're talking about n, which is greater than n0 meaning the starting n value, whatever it be. So if we're referring to any n value that is greater than the starting one, and the limit of the leftmost function, meaning the smaller function, and the largest function, the right one here, is equal to this value of L, well then the limit of b of n, this middle function, is also going to be equal to L. And again, I've kind of drawn out a little visual as to why this makes sense. We basically have these two outermost functions squeezing this middle one in between it. Basically, you can kind of think of it as compressing it to a certain value, which happens to be this L right here. Here is a nice little trick that we can use using the absolute value. This is very helpful when we have, for example, like -1 to the n. This trick right here, taking the limit of the absolute value of that sequence, if we have something like that, it's very useful to help us solve for what it is. But the important thing to notice about this little trick is that it's an implication, meaning it's like if P then Q, so like P implies Q in a sense, meaning that Q implies P, or like the backwards statement of this is not going to hold. So it only works, if you want to think about it, if you've taken like a discrete math course, you would understand that implication only works like in the if a condition, then an outcome holds, but it doesn't work in the reverse. So we can't just say, okay, if the limit of as n approaches infinity if a of n equals 0, then this is also true. Like, we can't say that. So it's important to notice that this is an implication, meaning it kind of only works if you want to think about it one way. So it only works if this condition is true, then this condition is true. It doesn't work the other way around. So again, all we need to do for this little trick is we want to take the absolute value of the nth term of the sequence, and if that equals 0, well then we can say that the limit as n approaches infinity of a of n also equals 0. So this would be a really good application of that little trick. Again, like I said, once we have this -1, that's a pretty good indicator that we're going to be using this little trick here with the absolute value. The example asks us to find out whether this sequence right here is convergent or divergent. So all we want to do is we want to take the limit of a of n as n approaches infinity. Well, that's going to equal to the limit as n approaches infinity of a of n. And what is a of n? Well, it's just given by this right here. Now, once we have this, what we want to do is we want to apply this trick right here. So we want to say that we want to find what the limit as n approaches infinity is of the absolute value of this sequence right here. So this right here is going to be equal to the limit as n approaches infinity of 1 over n. Now this limit is pretty easy to solve. It's going to equal to 0. Therefore, we can say that by this little trick right here, I won't be showing the actual proof for it, but just know that it is a little trick that helps with computations. So we say that, therefore, due to this trick, the limit as n approaches infinity of this sequence right here is actually going to equal to 0. So now to go over another example, this one is a little bit more important because as we move on towards series, you'll kind of see the connection. But we are asked for what values of r is this sequence convergent. So r is going to be the base. Now I'm going to break this down into a series of cases and we're going to kind of analyze them case by case. So case 1 is when r is just greater than 1. Now if we take like a sample of anything greater than 1, let's take 10. This the nth term is going to look like 10 to the n. And we can see that the limit of, for example, this sample of 10 to the n as n approaches infinity, well, that's going to be infinitely large, so it's just going to be infinity. Meaning the sequence, if r is greater than 1, is actually not going to be convergent because we're going to get infinity for this limit. Now for case number 2, if r is equal to 1, well then the nth term will look like something 1 to the n. And if we want to take the limit of that, of 1 to the n as n approaches infinity, well, we're simply going to get 1 because 1 raised to the power of anything is going to give us 1. So this sequence right here actually is convergent when r is equal to 1. The next one is when r is between 0 and 1. So r is going to be between 0 and 1. And in that case, like a sample value, let's just take as 0.5. So that's what the nth term could look like potentially. If we want to take the limit of any of those terms, right? Well, something like 0.5, that would just equal to 0. And the reason that is because we have a value less than 1, right? This, I've just used 0.5 as kind of a sample, but if we look at the restriction on r, it's that it's a value less than 1, but it's also greater than 0. So in that case, once we have a value within that range and we constantly multiply by each other, basically putting it to the power of n, well, the value is just going to get even smaller and smaller, and it will kind of converge down towards 0. So if we take a quick look, right here we have a half. Well, if we take a half and then multiply it by itself, well, now all of a sudden we get 1/4, and then if we want to apply another like iteration sort of, basically say n is 3, well, now it equals to an 1/8, and then if we want to keep doing that, now it's 1/16, and we'll see how we get closer and closer to 0. That's just the way these numbers work when they're between 0 and 1 like that. So because when we multiply them by each other, it'll keep getting smaller, we can say that the limit will approach 0. And so for that case, it actually is convergent because, again, we've reached a finite number. Now, how about for when r is actually equal to 0? Well, then the series will look something like 0 to the n. And if we want to take the limit as n approaches infinity of 0 to the n, well, that's simply going to equal to 0 because, well, 0 times 0 n times is still going to equal to 0. So again, if r equals 0, this sequence is going to be convergent. Now moving on to the negative numbers, what if r was between -1 and 0? Well, then we would have something like minus 0.5 to the n. And now is when we can apply that little trick that we've learned about the absolute value. So we are going to take the limit as n approaches infinity of the absolute value of this sequence. And now we can say that this is equal to the limit as n approaches infinity of what? Well, it's going to equal to 0.5 to the n, which is also going to equal to 0 because we have solved this limit before up here. So this is also going to equal to 0, and because the limit of the absolute value equals to 0, then we can say that the limit itself of this function right here will also equal to 0. So in the case that r is between -1 and 0, the sequence will also be convergent. Now what if r was equal to -1? Well, if r was equal to -1, the sequence would look something like this, -1 to the n. And in that case, we want to use the same exact limit trick that we've used. We basically want to take the absolute value of it. And in this case, we will get that it's equal to the limit as n approaches infinity of 1 to the n. And in this case, it's actually equal to 1. And if we go back to that little trick that we said that this only works if it's equal to 0. If the limit of the absolute value of a of n is equal to 0, only then can we conclude with this. But in this case, it's not equal to 0, meaning that this is actually going to be divergent. So the sequence for r equals -1 will be divergent. Lastly, we want to check if r is less than -1. In this case, we might have something like -10 to the n. And then we want to apply the same exact trick. We just take -10, the absolute value of -10 to the n. And we'll see that we get the limit as n approaches infinity of, let's say, like something 10 to the n, and that'll be infinity. So it's also divergent here. So we've kind of covered all cases. We've covered the ones, the zeros, the infinite values, let's say, and the values in between 0 and 1. So we've covered all cases with this little breakdown. And now all that's left to do is to pull out the information and see where the sequence is going to be convergent. So here on the first one, it's not going to be convergent because we approach infinity, meaning that the sequence will be divergent. However, on the next one, we can see that we approach a finite value. We approach 1, so therefore it will be convergent. Here it will be convergent because we approach 0. Here it will be convergent because we approach 0. Here it will be convergent as well because we approach 0 and we apply that trick. However, here we approach a finite value, but that's for the absolute value of that sequence. And because the absolute value didn't approach 0, then we can't conclude that the actual limit itself will approach 0. So we don't know what it'll approach, therefore it is divergent. And for the last one as well, it's going to be divergent because, well, we approach infinity and not a finite value. So we can conclude that this sequence right here is convergent when r is going to be between or equal to 1, and it will be greater than -1 as well. So therefore we can conclude that this sequence will be convergent when r is between -1 and 1, but it can actually be equal to 1, unlike mine. This is kind of the scenario when this sequence is convergent. Now, you might want to remember this because later on we will be dealing with this r value when it comes to series. So now moving on to increasing and decreasing series. We basically have like two of these classifications for it, whether a sequence is increasing or decreasing. It's pretty simple. I mean, it's the same as if we were talking about functions. So the sequence is called increasing if all the values, like I've marked it here, all the next terms in a sense are larger. So am plus 1 would kind of mean like the term after yourself. So let's say we have a sequence like 1, 2, 3. Well, this would be increasing because let's say we're on 1, the next term would be 2 and it's greater than 1. If we're on 2, the next term would be 3 and 3 is greater than 2. Therefore, this sequence would be increasing. The opposite applies for decreasing. Decreasing is if the term like before you, so before am plus 1, is smaller than the actual next term. I marked it here. Then we say that that sequence is decreasing. And again, something like 3, 2, 1, that sequence will be decreasing because when we're on 3, the next term right here is 2, and 2 is actually less than 3, so it's decreasing. If we're on the value 2, well, 1 right here is less than 2, therefore the entire sequence right here is going to be decreasing. And lastly, we call a sequence monotonic if it's either increasing or decreasing. So either one of the two, we say that the sequence is monotonic. The second last thing that we're going to talk about is bounds, and basically we want to check if a sequence is bounded, and we're going to explain what it means to be bounded. So like I wrote here, a of n, so the sequence is bounded above if there is a number m such that a of n is less than m for all n is greater than 1, meaning that there is some sort of number that is kind of the maximum of this sequence that no value, as we see here, for all n is greater than 1, all of these terms, a of whatever n, are all going to be less than m. So in a sense, there's this upper bound. In that case, if this condition is met, then we say that the sequence is bounded above. The opposite of that would be true if all of the values are going to be larger than some sort of m value, meaning we kind of have this minimum. In that case, we say that the sequence is bounded below. And we call a sequence bounded if it is bounded above and below. So that's the key difference. Before, we say that a sequence was monotonic if it was either increasing or decreasing. However, now we say that it's bounded if it's both. Bounded above and below, meaning there's some sort of maximum value and some sort of minimum value as well. Now, the last thing I want to cover is the monotonic sequence theorem, and it basically says that every bounded monotonic sequence is convergent. And I'm going to show you graphically why this makes complete sense, but we can sort of figure this out by breaking down the definition. So firstly, we see that the sequence is bounded. What this means is that if we were to draw like a graph, we would have some sort of like, let's say, maximum, and then it would also have some sort of minimum. So it would be bounded in between these two values, whatever they be. Let's call this, like, I don't know, a and b. So because it is bounded, the sequence has to stay within these two bounds right here. And also because the sequence is monotonic right here, well, that would mean that it's either increasing or it's decreasing. And it cannot be like both. It can't increase on some intervals and then decrease on other intervals. It has to be strictly increasing or strictly decreasing. So that would mean that either we kind of approach this upper bound like that, or we might approach this lower bound something like this. So it'd have to approach one of these bounds eventually because it is monotonic. It can't really like bounce up. You can't have something like this because that would not be monotonic. And also you cannot have something that would go towards infinity because, well, it is a bounded sequence. So that's it for today's lesson on sequences. I hope you enjoyed the video and learned something. If the video has helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.